my job for today, to start with, is to help you understand how radians work. Because when we do circle trig, it's always going to be radians. All right, to start with, get to this page, and then if you're in Notability, you have the ability to draw over something and then copy it over and over, right? Be really careful. Don't be as sloppy as I just was right there. Be really careful when you draw around it in the first place. Maybe use a circle tool. And then copy it so that you can copy and paste over and over and over again. And I want you to see how many Skittles it takes to go from here all the way to the edge. Did you guys get 7? If you haven't finished it, go ahead and finish it up and get 7. It should be 7 if you did it right. Now, does that mean that every circle ever would be 7 Skittles for a radius? Of course not. We set this circle up on purpose and the Skittle size on purpose so that it would be 7. Why is 7 such a lucky number? Well, I'll show you in a minute. But for right now make 7 Skittles this way. Including the one that's on the radius. And now connect it with one last radius. And if you go 7 and 7 and 7, what's different about one of those sides? Why can't I just say this is an equilateral triangle? It's kind of close. Yes?
One of the sides is curved.
Yes, and that's called an arc. In case you've forgotten the name for that, that's called an arc. So if you make it 7 by 7 by 7 with one of the sides being an arc, then you have just made 1 radian. The degrees in there, it's really close to 60 degrees, but it's not 60 degrees. So 1 radian is about 60 degrees. Do you have other things in your life that are kind of like that, where like it's close, but it's not exact? I'll give you an example. 1 inch. It's about 2 centimeters. Anybody know exactly what it is? Yes?
2.4.
I think you're right. Okay, here's another one. 1 yard. You know a yardstick and a meter stick are really close to each other? Would you agree that a yard and a meter are close, but not exact? Okay, how many inches in a yard? You guys should know that one. How many inches in a yard? 36 inches in 1 yard. Okay? You know how many there are in a meter stick? How many inches there are in a meter stick? Here's a meter stick. Would you agree? It goes over 39. Yep, a little more than 39. Okay, so some things don't just work out perfectly. All right, so it's not exactly 60 degrees. It's about 59 degrees. And I know that's annoyingly close, but it's not 60 degrees, but it's close. A little less. Okay. Next, I want to be able to teach you about, like if I want to say this angle right here, and let's say that I set it in degrees, and I said, I want it to be 120 degrees. And I wanted to figure out how many radians that would be. I'm going to teach you how to say this many degrees is this many radians. But to do that, we need to keep on drawing some more Skittles. Would you please continue the Skittle thing all the way across here until you get to here, which is be where 180 degrees is. If this is where 0 is, go all the way over to there, that's 180. I want to know how many skittles that is. Now, some of you have got it dialed in, and others of you, you're realizing your skittle thing is kind of off because you didn't copy it super well. Maybe you didn't use an actual circle. Did anybody get like really, really perfectly 7 in the first place? It like fit really nice and you got 7? Okay, a couple of you are yeses. For you guys especially, would you please count how many you get? The people that were like pretty dang exact on the 7. Count how many you get across. And remember to include that very first skittle. Like this skittle here counts in your 22 of them. Oh, I just said it. It should hit 22 skittles exactly. Did anybody hit exactly 22? Yep. A couple people that have been super careful. Now, I'd like you to think about 22 sevenths. Does anybody even know what 22 sevenths is? Yes? It's pi. Very good. Now I'd like you to think about this. If I had made you make some more of these, it would not have been exactly 3 of these. It would have been 3 plus a little bit more. It'd have been 1 radian, 2 radians, 3 radians. What's this last little bit? 3.14. It takes 3 plus a little bit more, 3.14. That's why this is pi radians. It's 3 radians is close, but it's not exactly 3. If it had been exactly 3, would you agree it would have been 21 and 7? You know, 7 and 21, that'd be exactly 3. But it's not 21 and 7. It's 22 over 7. So there's my proof. And it's just more, it's not a mathematical proof, but it's a, I don't know, it's kind of a fun way to show it. That pi radians is the same as 180 degrees. Pi goes with 180. Just like other weird combos, like 1.06 liters per flush. Have you ever seen that somewhere? It's on the toilet. There's this weird, like, with this weird decimal, well, 3.14 goes with 180. All right, I'm going to use one that everybody knows, 12 inches in 1 foot. A fact like this, same with 180 and pi, they're a fact, they go together. 12 inches in 1 foot can be used to convert, let's say I have 2 feet. Do you get then the feet would cancel and I get 2 times 12 is 24 inches? If you've never learned to convert this way, it is the best way to convert things. Say I have 3 meters. And some of you are like, yeah, I know that there's 100 centimeters in each meter. So I can do the conversion. Okay, but let's do it this way. 100 centimeters, 1 meter. Watch how cool this is. Cancels. 3 times 100 is 300 centimeters. What if instead I had given you 75 centimeters? You would times by, what's a fact about centimeters and meters that we know? There's 100 to 1. So you'd put 100 centimeters on the bottom. Why? So that this and this will cancel. And there's 1 meter here. This cancels this, and the answer is 75 100ths, 0.75. That's 0.75 of a meter. All right, let's make sure you really got this. 14 inches. I'd like you to use a conversion factor that you know about inches and feet to change that to feet. What's the conversion factor that you know? Well, it's always a fact about inches and feet. Tobias, can you tell me the fact that you're using?
12 inches or feet
Excellent. So where should the 12 inches go, on the top or on the bottom?
to the top.
If I do that, why will I not be very happy as I multiply this out? Inches aren't canceling. So we should actually put the 12 inches on the bottom. That's the only way that I know to tell you is you need to think about putting the inches so that there's one on the top and one on the bottom, and then you just got to do it that way. So what's that fact I know about inches again? 12 inches, 1 foot. And there we go, inches cancel. 14 twelfths of a foot. 14 over 12 feet. Could that simplify? Sure. 7/6 of a foot. That's what 14 inches is. Okay. The reason I'm practicing this is because half your assignment tonight goes like this. You have 120 degrees, and they ask you to change it to radians. You have to know how to do conversion factors. What's that fact we know about degrees and radians? Ruby, what's the numbers that go with degrees and radians? Hint, there's a pi involved. Got this or no? It's okay. There's a pi, and what's the other thing? So something goes here and something goes here. Yes?
It's pi and 180.
Excellent. Pi and 180. Why did I choose to put the 180 on the bottom, Gio?
So the units cancel out.
Exactly. So these cancel each other. My answer is 120 pi over 180. Why is that 120 on top? You can always put things over 1, right? And then couldn't the zeros cancel too? Yeah. So could you reduce 12 pi over 18? Sure you could. 6 goes in here twice. 6 times 2. This is 6 times 3. And the 6's cancel. 2 pi over 3. So we started with 120. We got 2 pi over 3 at the end. I'm going to do one more like that. Would you please write down 60 degrees? What's that fact we multiply by? Zodi, it's either 180 over... Oh, I haven't memorized this yet. Would everybody please say this after me? 180 goes with pi. I'm going to say it again. What goes with pi? 180. 180 goes with pi. Okay, so I just have to put 180 and pi in the right spots here. So what do you think I should put where? It'll go faster if you participate. 180 on the bottom so that the degrees will cancel. And there's a pi on the top. If you simplify this down, the degree will cancel the degree. And the 60 and the 180 will simplify. 6 pi over 18. Can you simplify that? I can. Can you? Elle, what do you get? Yep. So pi over 3 is the same thing as 60. Now I'd like you to think this through. Since 180 is pi, get how you can check that you're right. 180 divided by 3 is 60. See how that works? Pi is like 180. 180 divided by 3 makes 60. Yay, I did it right. Okay, I'm going to give you another one. 240 degrees. Let's change that to radians using conversion factors. This time, I would like you to compare how you set it up. Not even the answer, just how you set it up with the kid next to you. These 2 rows, you have somebody straight across from you, except for you, we'll go diagonal with the girls in the back. These 2 rows, straight across, unless you have to go diagonal. Just have you two compare, and I'd like you two to compare this one, and you two to compare. Okay. Let's compare the setup. See if they get it. See if you get it. So 180 goes here, pi goes here. It's always 180 and pi. Why did I put the 180 on the bottom? So this would cancel. They're gone. And then I like to go 6 times 4d. And this is going to be 6 times 30. And then it's 40 over 30. Oh, cross off the zeros. 4 pi over 3. Raise your hand if you had 4 pi over 3. Awesome. You now know how to convert from degrees to radians. But can you go from radians to degrees? 2 pi over 3 is in radians. Change it to degrees by multiplying by the right thing. So distracting. Put that up on the front ledge. I can carry it for you if you want. Just keep you from being distracted. Okay, let's see. Did you multiply by 180 over pi or pi over 180? Hill, what'd you say?
180 over pi.
I'm going to put 180 on the top and a pi on the bottom. As I look at it, I'm sure she's right. You know why? How do I know she did it right? Dodie. Yeah, these cancel. That tells me I'm doing it right. And now, I like to do the, if you can factor it, you should thing. And I'm going to say this is 3 times 60. Why did I do that? Because then the 3's will cancel. 2 times 60, 120. Boom. Who had 120? Okay, awesome. Then you're getting converting from radians to degrees. Now, the question is more to me, though, can you see it? Here's a circle. Draw that. That's how we always start. And then if I wanted to make 180 degrees, do you get I would just draw it like this straight over here? That's 180 degrees. What would it be in radians? Pi. Does pi and 180 go together? Pi's over there. What? Well, here's 1 radian. Here's 2 radians. Here's 3 radians. And it's a little more than 3 radians. 3.14 radians. All right. So that's pi, and it's 180 at the same time. It's like saying, I am 6 feet tall, and I'm 2 yards tall. It's the same thing. I'm just like saying it in different ways. 180 and pi. All right. So now, I'm going to draw you another one, and I want you to, this is like the most powerful ones. If I decided to make 3 30-degree angles, would you agree that I just made 30 plus 30 plus 30 makes a 90-degree angle? Okay. Then, what was each of those in radians? You said it was 30 degrees. Yeah, what is it in radians? Well, you could go off to the side and do that calculation thing, but would you agree that that's 1/6 of the way to here, which is pi? So it's 1/6 pi, which is pi over 6. See how I did that? 1/6 of the way to pi. So it's pi over 6. What's this spot? 2 pi over 6. What's this spot? 3 pi over 6, which reduces to pi over 2. This is 4 pi over 6, 5 pi over 6, and that is 6 pi over 6, because the 6's could cancel, right? So you got to start thinking this way, and I know it's kind of annoying, but after a while, seriously, you'll stop using degrees. You'll just be using radians. You'll be going, oh, that looks like it's about a pi over 6. Really. You'll get that good at it eventually. All right, so if I said, here's an angle, how many degrees is it? Well, I'd say 90 plus another 30 makes 120. 120 degrees, but we're not going to be using degrees. We're going to be using radians. How many pi over 6s is it? One pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6. See, that's a lot faster than having to go off and use that converting thing we just taught you. You can still do that, but when it's in the context of a circle, you got to start thinking this way. All right, now, the last element that I have to teach you today is this. Remember how I said this is called an arc length, the curvy length along the edge? There's a formula to figure out the arc length. And there's also a formula that helps you figure out the area of a sector of a circle. Do you get that's just a fractional part of the circle? It's the area of the whole circle, but just part of it. All right, so here's your last two things for today. First, we're going to figure out arc length, and that uses this formula right here, S equals theta r. And you better label each of these so they are not super intuitive. S stands for arc. I sometimes call it the SARC. I don't know why they labeled it S. I wish they would have labeled it A for arc. But S stands for the arc length. Theta is the angle. By now, I hope I've gotten you used to theta means angle, right? And it's the angle in radians. Those new things I just taught you, if you were going to only remember one thing, it was that 180 equaled pi. Okay, and then this last thing is the radius. Theta is always radians, though. If they give you degrees, you got to change it to radians. Okay, so here's a typical question. If the radius is 8, and this is 30 degrees, the first thing you'd have to do is go, oh, I can't let it be 30 degrees. I got to change that to radians. So yeah, you can go off to the side if you're not good at the circle thing yet, and you can go 180 over pi or pi over 180, and you can do it that way. Or you can say, okay, I think I got this. This is where pi is. It's 1/6 of the way to pi, so that's pi over 6. That angle right there is pi over 6. And then you go, the arc length, SARC length, equals the radians, pi over 6, times the radius is 8. 8 pi over 6. Can it be reduced? Sure it can. And should you reduce it? Always. 4 pi over 3. If you're like, that's a weird sounding length. Yeah, only because it's got pi in it. And if pi is just 3.14, couldn't you say it was about 4 times 3.14 all divided by 3? Yeah, you could. Which is just a little more than 4. Because, you know, 3.14 and 3 is almost enough to cancel each other out and make it 4, but it's a little bigger on top, so it's a little bigger than 4. So that distance is a little bigger than 4. Okay, so how would you find the area of a sector like this? Well, first you got to know that the area of the whole circle would be pi r squared. And do you agree that this is just a fraction of that pi r squared? Okay, so pi r squared, I wrote that funny. So pi times r squared. R is 8, so it's 8 squared. So it's pi times 64. 64 pi is the area of the whole thing. But we just want a fraction of that. We want 30 out of 360 of it. There's your answer with degrees. It's the degrees out of 360 times pi r squared. But what if it's in radians? Well, then it's a radians over 2 pi. Because 2 pi is like 2 half circles, right? Radians over 2 pi times pi r squared. All right, I'm going to show you one last one like that. You got a circle? You got that, and let's say it looks to me like that's about a 45-degree angle, so I'm going to say it is. Then that's 1/4 of the way to pi over here. That angle would be pi over 4. Let's say the radius is 8. Would you please figure out for me how long's that arc length? And separately, what's the area of the sector? Act like it's the ACT test, except weirdly, you get to check with the kid next to you. Figure out the arc length and figure out the area of the sector. And check with the kid next to you, please. I want to pause for a second while you try that. All right, so most of the kids have already answered that first one. They knew that the arc length would be pi over 4 times the radius is 8. So that simplifies down to 2 pi, which is about 2 times 3.14 is about a little more than 6, and that seems reasonable for that length. The area of the sector, you would do pi over 4 over 2 pi, because that's how many degrees a circle has total in it. And this is the part we have out of the total. And you times that by pi r squared. And in this case, that's pi times 8 squared, which is like pi times 64. And then I'm going to simplify this down here and say that's like pi over 4 times 1 over 2 pi. Where did you get that? See why I wanted you to understand a fraction over a fraction? Because of moments like this, you got to be able to say, oh, that's the first one times you flip the second one. That's why I really wanted you to get good at the basics before we even started. And then that means 1/8 times pi times 64, because this is 1/8. So that's 1/8 times pi times 64. That's going to work out nice. The 64 is 8 times 8. 8 will cancel. 8 pi. Who had an answer of 8 pi? Because you were right. 8 pi what? Well, this was an area, so 8 pi units squared. What's 8 pi? 8 times 3.14. It's a little more than 24. Maybe it's like 25. Okay. Now, big 1-minute review of everything I just taught you, except you could have never learned it this fast. You ready? If I take a circle and I draw where this is 8 and this is 8 and this is 8, that thing right there, that's an angle. It's called a what? Oh, come on. You don't know how many degrees that is? Or what it's called? That's a radian. All right, that's how big a radian is. All right, if that's 1 radian, how many radians would it take to get to here? Pi radians. That's the same spot as 180. Hence the whole 180 over pi thing. So if I give you an angle and I say it's like 3 pi over 4, you can go timesing by 180 over pi. Why the pi on the bottom? So that these would cancel. So that's changing from radians to degrees. And there were 2 formulas. S equals theta r. This is the arc length. Will be the radians times the radius. And in degrees, it's the degrees over 360 times pi r squared. And that's for the area of a sector. And if you want to do it in radians, it's the radians over 2 pi times pi r squared. That gives you the area of a sector of a circle with radians. I should really say this is just degrees right here. Instead of saying 30. 30 is common, but this is the degrees out of 360 times pi r squared. And the radians over 2 pi times pi r squared. Okay, that covers all of it. So now, it's your homework. I'd go here, and you should be able to do these. If you wanted to, you could do some of those for practice. But I have homework problems like that too. So, And here is their first homework problem. I don't like it, but it's better than it used to be. Believe me, it used to be about degrees and minutes and seconds, and it was really complicated, and we don't have to do that, so yay. Instead, they want to change it into radians. Well, did I teach you how to do this? Sure I did. It's just they have decimals on them. So you're going to have to use a calculator to get the final answer. So you're going to take this and you're going to times by, well, it's either 180 over pi or the other way around. Did I do it right? No. How do you know for sure? The degrees aren't going to cancel that way. So it's got to be the other way around. It's got to be pi over 180. You can write that down. Free help on your first one. Then I'd use a calculator to get the final decimal answer. And then it asks you to round it to the nearest hundredth. So you do that and you can check the answer key. I would definitely do some practice problems, especially of this page. Radians to degrees or degrees to radians. These kind of questions where they're whole numbers. You got to get good at this. It's going to happen a lot. This yellow page, numero uno. Got to know this. And you'll definitely be asked to find the area of a sector of a circle and the arc length of a circle. So I would definitely want to practice some of those. Now you have probably at least 3 questions of your next test. And the page is up to here. The last question is a really good question. But it's kind of tricky to figure out. But it's really cool. If you want to explore, good at math, you might like that one. All right, and that's all I've got for you for today.